In the middle of the 20th century, some of the busiest rail territory in America operated under a simple but absolute rule: no diesel locomotives in the tunnels. Grand Central Terminal, Penn Station, and the approaches leading into Manhattan had banned them outright. The reason wasn't regulatory overreach, it was survival. Diesel exhaust in enclosed spaces had already caused deaths. After a 1902 collision in the Park Avenue Tunnel filled with steam, locomotive smoke killed 15 people. New York Central electrified its approach to Grand Central. When diesels arrived decades later, the same ventilation concerns applied. The fumes, the fire risk, the carbon monoxide, none of it was acceptable in tunnels built for steam and later electrified for safety. But the railroads still needed to run diesel trains into the city. Freight could be handed off. Passengers couldn't wait. The New York, New Haven, and Hartford Railroad faced this problem more acutely than anyone else. Its trains ran on diesel power through Connecticut and lower New York State. But to reach Grand Central, they had to enter electrified territory where diesel operation was prohibited. The traditional solution was a locomotive change. Diesel power brought the train to the edge of electrified territory, stopped, uncoupled, and an electric locomotive took over for the final miles. This cost time, labor, and money the New Haven didn't have. The solution wasn't a new electrification project. It wasn't a regulatory exemption. It was a locomotive that could run on diesel power in open territory and switch to electric power when it reached the third rail. This was the EMD FL9, a machine designed not to break the rules, but to survive them. Before we continue, if you think our content is unique and informative, please leave a like and subscribe. It really helps support the channel. Also, make sure to share the video with other train fanatics out there. The problem the FL9 solved didn't start with the New Haven. It started with New York City's decision to electrify its rail approaches after the 1902 Park Avenue Tunnel disaster. That collision, caused by a locomotive engineer unable to see signals through thick steam and smoke, led to 15 deaths and public outrage. The response was electrification. By 1906, New York Central had converted its approach to Grand Central to third rail electric operation, eliminating steam locomotives from the tunnels. When diesel locomotives arrived in the 1930s and 40s, the same restrictions applied. Diesel exhaust contained carbon monoxide, unburned hydrocarbons, nitrogen oxides, all dangerous in confined spaces. The tunnels leading into Grand Central and Penn Station had limited ventilation. Allowing sustained diesel operation would have required massive infrastructure upgrades. It was cheaper and safer to simply ban them. This created a geographic boundary. North and east of the Harlem River, diesel locomotives could operate freely. South of that line, only electric traction was permitted. For freight railroads, this was manageable. Trains could be handed off to electric switchers at the border. For passenger railroads, especially those running through service from distant points, the operational cost was severe. Every train had to stop, change locomotives, and proceed. The delay alone could add 20 to 30 minutes. Worse, it required maintaining two fleets, diesel locomotives for the outer territory and electric locomotives for the final approach. The New Haven Railroad ran passenger trains from Boston, Springfield, and intermediate points, all diesel-powered, all destined for Grand Central. The locomotive change at Woodlawn or Mount Vernon East became a daily bottleneck. The New Haven considered its options. It could build a larger fleet of electric locomotives and extend electrification further north, but the railroad was already in financial distress. It had deferred maintenance, aging equipment, and mounting debt. Capital for infrastructure expansion didn't exist. It could accept the delays and continue swapping locomotives, but this hurt schedule reliability and increased labor costs. Or it could find a locomotive that operated in both modes. No such machine existed in the United States in the early 1950s. European railroads had experimented with dual-mode designs, but American conditions were different. The New Haven approached EMD with the problem, and EMD responded with the FL9. The FL9 was not an elegant machine. It was a compromise. EMD started with the F-Series carbide design, already proven in passenger service across the country. The F unit was a streamlined cab-equipped locomotive built on a two-axle truck configuration. It was reliable, relatively lightweight, and widely supported, but adding electric capability required substantial modifications. The locomotive needed space for third rail pickup shoes, electrical contactors, protective equipment, and additional wiring. EMD lengthened the frame by 4 feet compared to a standard F unit, stretching the locomotive to 59 feet. This gave it an unusual, slightly unbalanced appearance. The proportions were off, longer than it looked like it should be, but not quite long enough to add another axle. The result was a locomotive that looked like an F unit that had been pulled at both ends. Under the hood, the FL9 carried an EMD 567C prime mover, a 16-cylinder 2-stroke diesel engine producing 1,750 horsepower in diesel mode. This was conventional EMD technology, shared with other passenger locomotives of the period. Power from the diesel engine drove a main generator, which supplied DC current to 4 traction motors, 1 per axle. The locomotive rode on 2 Blomberg B trucks, the standard EMD design. In diesel mode, it operated like any other EMD passenger unit, reliable, straightforward, and familiar to crews. The electric capability was grafted onto this diesel platform. The FL9 carried third-rail pickup shoes mounted on the trucks. When the locomotive entered electrified territory, the engineer manually raised the shoes to make contact with the 600-volt DC third rail. Current flowed from the third rail through protective circuitry and directly to the traction motors. The diesel engine shut down. The locomotive now drew power externally, like a pure electric. The transition was entirely manual. There was no automatic detection, no computerized switching. The engineer had to know where the third rail began, slow the train, raise the shoes, confirm electrical contact, and shut down the diesel. The process required training, judgment, and attention. Done correctly, it was smooth. Done incorrectly, it could damage equipment or leave the train stranded. The electrical system wasn't sophisticated by later standards. The FL9 had no onboard conversion equipment. It didn't transform voltage or rectify AC to DC. It simply took 600-volt DC from the third rail and fed it to the traction motors, which were already designed to operate on DC. This simplicity was deliberate. The fewer components between the third rail and the wheels, the fewer things that could fail. But it also meant the FL9 was locked to 600-volt third rail systems. It couldn't operate under overhead catenary. It couldn't adapt to different voltages. It was purpose-built for one very specific operating environment. The extra equipment added weight. A standard F7 passenger unit weighed around 230,000 pounds. The FL9 came in at roughly 286,000 pounds, about 28 tons heavier. This additional weight per axle affected ride quality and increased wear on the trucks. The locomotive had a reputation for being somewhat rough riding, particularly at higher speeds. Crews noticed. Passengers, if they paid attention, might have noticed too. But it was within acceptable limits, and the operational flexibility it provided outweighed the comfort penalty, one feature often misunderstood. The FL9 did not run both power sources simultaneously. It operated in diesel mode or electric mode, not both. There was no hybrid operation, no boost from combining diesel and electric output. The transition was binary, diesel on, electric off, or electric on, diesel off. This limited its flexibility, but simplified the design. The locomotive didn't need complex logic to manage 2 active power sources. It just needed reliable switching between them. In daily operation, the FL9 became a known quantity. Crews learned where to make the transition. Approaching the Harlem River, the third rail began. The engineer throttled back, brought the train to a crawl, and raised the pickup shoes. If contact was good, the ammeter showed current draw. The diesel could be shut down. The train proceeded into Grand Central under electric power, silent except for the hum of the traction motors and the rhythmic clack of wheels on rail. No smoke, no exhaust, no violation of the rules. The transition wasn't instantaneous, but it didn't need to be. Passenger trains. Approaching Grand Central were already slowing for interlockings, speed restrictions, and station approaches. The extra few seconds to switch modes blended into the normal deceleration. Passengers rarely noticed unless something went wrong. Crews, on the other hand, had to stay alert. Third rail gaps, switch frogs, and dead sections required careful throttle management. Losing power mid-transition could stall the train. It didn't happen often, but it was always a possibility. In reverse, leaving Grand Central, the process repeated. The train departed under electric power until reaching the end of the third rail. The engineer lowered the shoes, started the diesel, confirmed power, and continued north. Again, the timing had to be precise. Start the diesel too early, and exhaust filled the tunnel. Wait too long, and the train might lose momentum on a grade. Crews developed a rhythm. They knew the landmarks, the mileposts, the feel of the transition. The FL9 rewarded familiarity. Performance was adequate, not impressive. In diesel mode, 1,750 horsepower was sufficient for the New Haven's passenger schedules, but not generous. The railroad typically ran FL9s in pairs on longer or heavier trains. This gave 3,500 horsepower, enough for sustained speeds in the 70 to 80 km/h range with a 6 to 8 car consist. In electric mode, power draw from the third rail was limited by the electrical system's capacity and the third rail's own limitations. The FL9 could pull reasonably well, but wasn't designed for rapid acceleration or high sustained speeds under electric power. It was designed to keep moving and reach the terminal without stopping. Winter presented unique challenges. Snow and ice on the third rail reduced electrical contact. The pickup shoes could scrape clear a light accumulation, but heavy ice buildup caused problems. If electric power became unreliable, the engineer could drop the shoes and revert to diesel mode. This was technically a violation of the no diesel rule, but in practice, short-term use to keep the train moving was tolerated, especially in emergencies. The FL9's dual capability gave crews a safety margin that pure electric locomotives didn't have. If the third rail failed, they weren't stranded. Reliability was a mixed story. The diesel side of the equation was proven EMD technology. The 5.67C engine had thousands of hours of service data. Parts were available. Mechanics knew the platform. The electric side was less familiar. Third rail shoes wore down from contact and had to be replaced regularly. Electrical contactors could fail. Wiring exposed to the elements corroded. The FL9 required more maintenance attention than a standard diesel, but it wasn't dramatically worse. Railroads factored the extra upkeep into operating costs and accepted it as the price of access. Crews generally respected the FL9. It wasn't beloved the way some locomotives are, but it was understood. Engineers appreciated its predictability. When maintained properly, it did what it was supposed to do. When neglected, it punished operators with electrical faults and rough running. This created a feedback loop. Railroads that kept their FL9s in good condition got decent service. Railroads that deferred maintenance got increasing failures. The FL9 survived far longer than anyone expected. It was designed in the early 1950s, built between 1956 and 1960, and remained in active service into the 1990s. Some units lasted even longer, operating well into the 2000s in work-train service. This longevity had nothing to do with superiority. The FL9 wasn't faster, more powerful, or more efficient than later locomotives. It survived because it solved a problem nothing else could solve affordably. The New Haven Railroad collapsed financially in 1961 and entered bankruptcy. It limped along under trustees until 1969, when it was absorbed into Penn Central. Penn Central itself failed in 1970, the largest corporate bankruptcy in American history to that point. The FL9s passed to Conrail in 1976 and then to Metro North when commuter operations in the New York area were reorganized in 1983. Through all of this chaos, the FL9 kept running. Replacement would have required either buying new dual-mode locomotives, which didn't exist in suitable form, or separating diesel and electric fleets, which would have reintroduced the delays and costs the FL9 had eliminated. By the 1980s, the FL9s were aging. EMD no longer built them. Parts were becoming scarce. But Metro North had inherited a fleet of 58 units, and they were still needed. The alternative was investing in new dual-mode technology or accepting operational compromises. Neither was attractive, so Metro North kept rebuilding them. Engines were overhauled, electrical systems were refurbished, trucks were repaired. The locomotives received updated paint schemes and minor upgrades, but fundamentally, they remained 1950s technology operating in the 1980s and 90s. Other dual-mode locomotives did eventually appear. GE built the P32ACDM Genesis in the late 1990s, a modern dual-mode diesel-electric capable of running under third rail or overhead catenary. These were far more sophisticated than the FL9, with microprocessor controls, AC traction, and higher power output. But they were expensive, and Metro North didn't replace all the FL9s immediately. The older locomotives continued in service, increasingly relegated to off-peak runs, work trains, and backup duty. The The last FL9s in regular passenger service were retired around 2009, more than 50 years after the first units were built. Why did no one else build a comparable machine? The FL9's operating environment was unique. Most railroads didn't have the specific combination of long diesel territory leading directly into third-rail electrified terminals. Those that did either had the capital to maintain separate fleets or avoided the problem through operational changes. The Long Island Railroad, for instance, used diesel locomotives in its eastern territory and electric multiple units in the electrified zone, with no through service. The New Haven's insistence on single locomotive through trains created the demand for the FL9. Without that demand elsewhere, EMD had no reason to continue production. The FL9 also represented a specific moment in railroad electrification history. In the 1950s, third-rail DC systems were common in the United States. By the 1970s and 80s, new electrification projects favored overhead AC catenary, which allowed higher voltages, better reliability, and easier maintenance. The FL9's dependence on 600-volt third rail made it obsolete as infrastructure evolved. Modern dual-mode locomotives are designed around overhead catenary, not third rail. The FL9's technology became a dead end. Another factor was institutional knowledge. By the 1980s, Metro-North had crews who had operated FL9s for decades. They knew the quirks, the maintenance needs, the operating limits. Training new engineers on FL9s was easier than introducing a completely new locomotive type. This created inertia. As long as the FL9s kept running and parts could be fabricated or sourced from stored units, there was no urgent reason to replace them. Eventually, attrition forced the issue, but it took decades. The FL9's survival also reflected the financial realities of commuter rail. Metro-North, like most commuter agencies, operated on tight budgets. New locomotives cost millions of dollars each. Keeping the FL9s running cost less, even with increasing maintenance expenses. When funds were limited, deferring replacement was the rational choice. The FL9s became a symbol of deferred investment, but also of pragmatic resource management. The FL9's legacy is not one of technical brilliance. It was never the best locomotive in any measurable category. It was slower than dedicated passenger diesels, less powerful than dedicated electrics, and more complex than either. Its design was dictated by constraints, weight limits, clearance restrictions, voltage compatibility, and the need to fit within an existing fleet structure. But it worked. And because it worked, it kept running long after sleeker, more advanced machines had been retired. What the FL9 demonstrated was that railroad engineering is often about access, not performance. The New Haven didn't need the most powerful locomotive. It needed a locomotive that could reach Grand Central without stopping to change power. The FL9 provided that access. Everything else, ride quality, fuel efficiency, maintenance complexity, was secondary to the ability to enter electrified territory. This principle has been largely forgotten. Modern locomotive development emphasizes power, efficiency, emissions, and computerized control. These are important, but they assume that access is a given. The FL9 operated in an environment where access was restricted, and the ability to navigate that restriction determined whether a locomotive was useful or irrelevant. No amount of horsepower mattered if the locomotive couldn't enter the tunnel. The FL9 also illustrated the limits of standardization. EMD built thousands of F units, all variations on the same basic design. The FL9 was an outlier, a custom solution for a specific problem. Only 60 units were built, all for two railroads, 54 for the New Haven and 6 for the Consolidated Diesel Electric Corporation, a commuter rail operator later absorbed into Metro-North. This small production run made the FL9 economically marginal for EMD. There was no export market, no follow-on orders from other railroads. The FL9 existed because the New Haven needed it, and it disappeared because no one else did. In the end, the FL9 survived not because it was advanced, but because it was allowed to go where others were not. It navigated a regulatory boundary that would have otherwise required separate fleets, locomotive swaps, and operational delays. It did so with 1950s technology, manual controls, and mechanical simplicity, and it kept doing so for 50 years, long after the conditions that created it had faded from memory. That durability, more than any technical feature, defines what the FL9 was: a machine built to solve a problem, and stubborn enough to keep solving it until something better finally replaced it.